Hello everyone and welcome to my talk entitled Fast Physics for Robotics in Games. My name is Michael Franco. I'm a postdoc in the image analysis section of DIKU. The talk will be a brief overview of physics simulation for robotics in games. We'll give you a bit of insight into my own research and at the end put it in perspective with the current state of the art and the trends for the future. So I'm originally a software engineer. I've started with mobile games, writing them in Java before the smartphone era, and then moved to physics middleware with Havoc in Dublin. Then I moved to Crytek in Frankfurt, working on their physics engine and where I wrote a class simulator. And later I worked at Ubisoft on their internal physics engine. I graduated more than 10 years ago from University of Copenhagen in Bucharest. I had a thesis on real-time simulation. I joined a bit later to do my PhD, which I finished in 2016. And starting with last year, the beginning, I joined DIKU with a Marie Curie postdoc grant. And here I'm working with Kenny Elleben, who is a world-renowned expert in simulation. So what is physics simulation? What do I mean by that? In this context, we're talking mostly about dynamic simulation of mechanical phenomena. And by that, I mean rigid bodies and cloth and soft bodies. And it could also be fluids, but we're not talking about fluids here. So there are two types of simulations. And these are real-time and offline simulations. And it could be real-time for games. That's your first thought, I imagine. But there are also serious applications for real-time physics. And then offline simulation has been around for decades in engineering and more recently for movies. And a lot of the time, these two types of offline simulation use this method called the finite element method, which is quite popular for deformable bodies, but it's not the only one. So I wanted to list a few of the simulators that are out there and companies building them. It's not all of them, and I haven't included, for example, Mujoko or NVIDIA Flex because I couldn't find the logo for them. But they are relevant to the topic of this presentation. So you have all kinds of engines. You have game engines, you have engineering engines, you have FEM engines for medical applications, you have open source ones, you have commercial ones, so all kinds of engines. So there are quite a few of simulators out there. So what do I mean by fast physics? And of course, the first thought that comes to your mind is games, but that's not the only application. And there are videos on YouTube, like this one here from CM Labs, which shows you a real-time bulldozer trainer. Or you have this Humvee simulator using Chrono, or you have this assembly line using XDE with haptics and VR. And then you have some of Miles's work in Flex for soft robotics, or Erwin's work in Bullet for robotics at Google. And even the fashion industry requires real-time simulation for cloth. So a lot of demand out there for game-like technology. So speaking of games and this trend of taking game tech and bringing it over to serious applications, let's see how the state of the art looks in there. And I chose cloth simulation. And this is the game I was telling you about that I wrote a cloth simulator for. And here you have the latest Assassin's Creed Odyssey, which was using the in-house cloth simulator that I worked on in the last few years. So as you can see, there are some nice effects in there on the tunics and on the other characters and scarves and leather straps and all that. Not a lot of it. And the thing is that this is because it's running on CPU, so the time budget is very tight. So somehow surprisingly, the physics is still running on CPU in games because there is no room on the GPU. So it's mostly the rendering and the machine learning communities that are using the GPUs nowadays, and not so much the simulation community. Right. So moving forward, as I said, I took a break at some point and I did my PhD. And given that game physics is not so exciting as 2 decades ago, I embraced the future and I looked at multi-body dynamic simulation, basically taking all these types of bodies and simulating them under one big Uber solver. So as you can see here, I managed to do that, partly at least, using constraints and constraint solvers and a special subset of it called position-based dynamics. And I managed to show that even if it is approximate position-based dynamics, it's not a hacky way of simulating dynamics. It's still not the best approach, and I'm currently working on a replacement for it called mixed FEM when simulating volumetric deformable objects, but otherwise it's quite a good method and quite a good paradigm to start from. Right. So this brings me to my current project. And this is about soft robots. As the title tells you, it's made up of soft parts, deformable or compliant parts, which can be actuated in various ways. For example, using cables or inflating them with pressure. And this is the subject of my European postdoc project. And already Kenny was working with some of his students in the workshop that exists here at DIKU. And this is showing a soft robot, simple air chamber soft robot inflating. And the problem with simulating soft robots, which is the topic of my research, is that it's slow because there are so many degrees of freedom to simulate for, even if you discretize. So this is where game physics comes to the rescue. And we're hoping that all those optimizations and shortcuts taken in physics will solve the problem, partially at least, while keeping the simulation still accurate. So the ultimate goal is to use this kind of simulations in a reinforcement learning context, where you need to run these many episodes in parallel for training a policy, and you need them to be very fast. You need them to be even faster than real time. So this is, again, why fast physics is needed. So to give you some examples of the kind of silicon robots we're building. So these are cable-driven, some of them, and this is Max, an ex-master student, currently a PhD, building such a robot and curing the silicon into molds. And pay attention that this silicon rubber is an incompressible material with a Poisson ratio very close to 0.5. And basically this will be an important thing to keep in mind when simulating the robots. So physics simulation is a broad topic, and the mathematics behind it is not trivial. We don't have time to go through it in this presentation, but I said I would put on a slide basic ingredients of a simulator. So you have here the differential equations and integrating them. You have constraints, you have springs, you have rigid bodies, you have a continuum mechanics of bodies, and then you have contact and friction to couple all of them. And finally, we have the finite elements paradigm for approaching continuum mechanics, which is just a way of interpolating the deformation field using discrete points. So yeah, these ingredients make up a simulator. So I wanted to give you an idea of what is the basic anatomy of a simulator. So you have a black box taking positions and velocities and spewing them out after a time delta t, evolving in time given forces and boundary conditions and all that. The problem with this view is that most explicit integration schemes don't work. They are not stable. So most people, including myself, use implicit integration schemes, which usually boil down to solving a system of nonlinear equations, or alternatively minimizing discrete objective energy. So this is how you end up with the idea of a solver. So the solver is the core of everything in a physics simulator. So you have a constraint solver, or a mass spring system solver, or in our case, a finite elements solver. And usually you want them all together to work together, which is the topic of what I'm going to talk about. And to sum up, these are my research interests. So I'm gravitating around the applications in soft robotics, but underneath it all, it's the idea of multi-body dynamics with deformable bodies and rigid bodies and frictional contact between them. And the paradigm I'm using is that of constraint dynamics and the ideas from position-based dynamics, which I used in games and my PhD research. And I found a middle ground between PBD and accuracy, and this is called mixed FEM, which is taken from the engineering literature. And this also clarifies a bit more the equivalence between constraints and elasticity when you add a bit of compliance to the constraints. So in the end, what I like to achieve is an engineering task, which is to build those high fidelity solvers, as I call them. And these need to be unified in terms of multi-body dynamics, and they need to be fast and stable, just like in games. And they need to be a bit more accurate, not just plausible. So this is clearly a compromise. You cannot have it all, but you can try. And this is what I'm doing currently. So yeah, this brings me to the finite element method, which I'm currently using to simulate soft robots. In a nutshell, and it's very hard to put FEM in a nutshell, but what it's all about, it's continuum mechanics is trying to encode the deformation of very small chunks of matter into this deformation gradient, which you're seeing on the right-hand side. And the finite element method just finds a way to use some finite sized chunks of geometry. And for that, it uses triangles or tetrahedra in 3D or boxes. And it codes that deformation gradient matrix using interpolation. So what is wrong with this picture? Why is it not working? Like, why are we not using it and optimizing it? And yeah, sure, yes, of course, we can do that. And a lot of people are doing that, and I am doing it too in my own code. But let's run an inflated tube simulation, which is common in inflating soft robots. And you have here a standard FEM simulation for our nearly incompressible silicon rubber. And looking at it, you don't know if it's good or bad. And that is a good question. Is it a good solution? And somehow by serendipity, let's call it, while I was trying to solve this problem using constraints and using some kind of PBD form of FEM, I found out the mixed FEM method in engineering books. And I ran the simulation and I got this. And clearly this looks better. And I know it's better because by reading those books, I realized that mixed FEM solves a problem called locking, which you can see on the left-hand side in the standard simulation. So locking means that the object is stiffer than it should be and is deforming too little. And this was a great discovery. And basically that showed me that you can do both FEM as a constraint dynamics problem and also solve the locking problem. So what is locking? Locking is a phenomenon that happens when you're trying to preserve volume or area. So you have these two triangles, 1 and 2, and only one point can move, the hollow circle. And you can see that if you want to preserve area, triangle 1 can only move vertically, whereas triangle 2 can only move horizontally. And being coupled together, that means they won't be able to move at all, so they lock. So to tell you more about mixed FEM and how it works, in simple terms, it's mostly about adding extra variables, which give you extra degrees of freedom and extra slack to the system, so it can deform more. So you put at the nodes extra variables, which are in fact the pressure values. And when you look at the mathematics of it, you see that you're transforming the problem from a simple linear system, you're transforming it to a saddle point problem system, which is basically the prototype of constraint dynamics. So now we're solving a constraint dynamics problem. And this is good news because we know how to solve constraint dynamics problems, or sort of. And we can put all kinds of constraints together, like ball and socket joints and contact and friction and distance constraints and all that. So this is good news. And I wrote 2 papers on this topic, and one of them was published last autumn, and the other one is currently under review. And this was the first paper, and it was basically using this corrotational approach for approximating nonlinear deformations. And this only implies solving a linear system. So it's pretty fast and accurate. And as you can see, it's pretty realistic compared to reality. And the standard method locks. And this is the video which accompanies the paper. And you can see things in a more dynamic context. So you can see that my method gives a wider range of deformation and more oscillation to the robot. And here you can see it in slow motion. And also the method is valid. It's acting just like standard corrotational methods. So there are no volume artifacts, and it works well under rotations. And even more so, it is much more stable for nearly incompressible materials compared to the standard corrotational method. So already we're seeing that the standard corrotational methods widely used in games and real-time physics nowadays are not great for incompressible materials. And in the next paper, I took this further and I showed the same things for the nonlinear materials, and especially for the neo-Hookean materials, which are quite popular. And you can see here in this comparison that the closer you get to full incompressibility, basically the standard method locks, which is very bad news because a lot of people are using it, and a lot of people don't know about this issue, and those who know are hacking it, are cheating. They are using a smaller Poisson ratio, like 0.45. So basically they are simulating the wrong physics. So using this this method that I developed for nonlinear materials using the mixed formulation, I managed to do some preliminary tests for inflating soft robots, and the results look promising so far, and there is still much more work to do. But already I'm seeing better results in terms of numerical convergence compared to standard methods. And this is our things that people don't talk about, like a Newton solver for the standard FEM Neo-Hookean material is having a hard time converging in these scenarios, whereas my method is doing so much better. So it not only avoids locking and gives you the true deformation of the robot, it only converges, it also converges much faster. So these are good results already in terms of fast physics for soft robots. And the problem is that in those inflating air chamber scenarios, we're still not doing good. And a lot of people are seeing this problem. So no matter how good your solver is and how robust it is and how well it converges, it's still prone to inverting. So elements inverting are scenarios like this one, where you take this node, for example, and it's being pushed so much by an external force that it crosses the opposite edge or face in 3D, and it ends up on the other side as drawn here. And basically, the area here drawn in blue becomes negative compared to the original one. So this is what we mean by an inverted element. And there are some ways of dealing with it. Some people in computer graphics hack the material formulations, because some materials that you can have not even defined for that domain. But many times the solver cannot even handle that, and the simulation can crash or the mesh can explode. And my solution is to identify the fact that you always need to not invert. So you always need to keep your area positive, and you need to avoid getting into the inverted domain in your solver. So using that idea, I made some preliminary tests, and I'm seeing very good results, and I'm continuing my research in that direction and hoping to publish something as soon as possible. So having attacked both inversion and locking, which I think they are essential problems when simulating soft robots, and standard FEM methods are not exactly ready for that, especially simulators that are optimized for real time. That brings us indeed to the optimization issue and how we can get a solver that does this simulation fast, which is the topic of our presentation. And there are several ways of doing it in a fast way. So one way is to go at the model and the numerical method and obtain a good convergence rate, which I obtained with the mixed FEM. But you also want to have something like you do in games and terminate earlier than convergence is achieved. And that's another way of speeding up a simulator, even if it's not accurate anymore. But you do want that, and obtaining such a solver for FEM is still a tricky business. And you also want the solver to be robust, like in games. You never want it to blow up. You always want it to recover from difficult situations like locking. And yeah. And you want it to be accurate because you don't want to learn crap, and you don't want to simulate the wrong physics, which I already shown to you with the locking scenario. You don't want to use Neo-Hookean standard FEM and incompressible materials. And you have to be able to use highly nonlinear materials like they're in reality. And yeah, and even if you go low res, it's fine, like even if you're not completely, you're only like simulating the broad lines of simulation. You don't want to simulate the wrong stuff. So as I showed you for the spine soft robot and the inflating cube, these are very important things. And of course, ideally, we would want to validate all this stuff, which not a lot of people are doing. And we are trying to do that, but there is still much work to be done. So yeah, I already talked about this multi-body dynamics unified dream and trying to accomplish it, and the fact that you also have to put friction in there, which is kind of hard to model properly. But one thing I wanted to stress was the idea of a solver being simple, because if it's simple to understand, then it's simple to implement. And if it's simple to implement, then it's easier to parallelize it and put it on the GPU or multi-core or whatever, and then it's easier to maintain it. And I think this is more important than building these very complex solvers like a Newton with a line search, and I don't know, maybe even more than complex than that, which has like an incredible convergence rate, but it's so hard to code and parallelize. And even like a solver like Gauss-Seidel, which is so popular in rigid bodies and cloth, even that has a lot of problem being parallelized. So my idea right now is that you better use a thing like a Jacobi solver or a steepest descent solver or a mean res solver and parallelize it and just use some brute force approach on a parallel architecture to achieve the simulation. And this idea also drew me to write a solver for the mixed FEM, which uses something called like a dual ascent, or basically that's a flavor of the method of multipliers, also known as augmented Lagrangian method. And people who are familiar with ADMM may know about this stuff. And this is much simpler solver to implement. And this is currently under review, and I'm currently developing it for the general case of multi-body dynamics. So of course, there are still open problems. I haven't touched upon collision detection, which is still an unsolved problem for triangular meshes. I still have to implement cable actuation. I still have to do validation, and we have this computer vision set up in the workshop that we're trying to make it work. It is known the system identification is a hard problem, and we also try to tackle it. And then there is the question of how to attack this robotics control problem. Should we use inverse dynamics or should we use forward dynamics in a reinforcement learning context? And even in that case, how do we design a reward function? And even more, how do we choose a state and action space from an infinite dimensional space? And of course, I would have liked to talk more about the software engineering side of things, which is pretty much what I'm doing. But there is not a lot of time for that. So most of the coding I'm doing is C++, and I learned a lot of lessons out of it. It seems that people need the code to be exposed to Python nowadays. I'm still to do that. And I think that some important lessons are that you should always keep optimization to the end. And one thing that I thought it was not so much needed in simulation, I'm starting to believe it's crucial, it's testing your code and making sure you're not breaking your simulation code. And I don't want to end this talk without mentioning the work of two master students I'm supervising, Anders and Jakob. And basically they are solving a computer vision problem. We have these two Intel RealSense cameras, which are taking RGB and depth data. And we are assuming that the cameras can be at any orientation from each other and they can be moving from each other while recording the scene. And basically they are aligning the 2-point clouds coming from the two cameras. And the hope is that we will be able to use this system to track soft robots without markers and then use the aligned point clouds to do validation, parameter estimation, and control policies. And keep in mind that this is not ICP, so this is not a registration problem per se, but this is more an alignment between the two cameras using some special calibration objects in the scene. And this brings me to the end of the talk and the conclusions. So again, fast real-time physics is crucial for nowadays progress in robotics. It even needs to be faster than real time. And of course, you can do that by using smaller scenes. And yeah, and giving all the resources to it. And of course, you need to be stable. Just like in games, you do not afford to track your simulations and have them broken while running a reinforcement learning algorithm with many episodes running in parallel. And the dream is that the simulator is a unified one, doing all the multi-body dynamics under the same umbrella. And yes, maybe a conflicting goal is to have all this physics being accurate. And I've shown you some of the ways of achieving this, and there are lots of other ways, and there are standard ways and non-standard ways like constraints. And a few people are doing this. One is Miles Macklin, who's also part of our group, and he's working for NVIDIA. And there are other people at Pulit and Google and other simulators working on these things. So this is still work in progress. One thing that I would like to say is that I feel that the time for big monolithic simulators is a bit over, and especially commercial ones. I think we need a lot of open source code, and it needs to be broken down into modules, and such that people can use different pieces in their Python code and mix and match and hack it and have different methods and compare them. So yeah, fast physics is hot at the moment in the robotics. Most of the research there is oriented about the machine learning aspects of it, but simulation is important and you need to know about it if you want to do a good job. And who knows, maybe all this technology will explode in a few years in robotics and might come back to the games industry through the back door. And it may be coming through the AR, VR part of things where physical realism is more important than nowadays games. But I'm not sure how many years that would take. And I'm not sure when then it's going to happen and what was going to happen on the hardware side. So not sure. Thank you for attending my talk and paying attention. Do not hesitate to contact me at my email address, or you can find me all around the web and social media. Just Google my name. There is also a simulation course at DIKU if you're interested. It's called Simis. Kenny is teaching it together with other people. And do not hesitate to contact him for more details. And the same for research topics, both me and Kenny. And there's also some open source code, which I'm currently developing. And it's up on GitHub. And I'm also open for questions. Thank you again. And please go ahead with the questions, especially if you're a student from DIKU.